Hello Noddies. So far in this series, our common source amplifier could amplify almost every signal within its bandwidth. But what if I want to amplify only one range of frequency and reject everything else? For example, only voice frequency in a microphone, only one radio station in a receiver, only a particular sensor signal while rejecting the noise. This is where a bandpass amplifier comes into the picture. Today, we are going to convert our ordinary common source amplifier into a bandpass common source amplifier simply by adding two capacitors. And surprisingly, we won't even touch the transistor sizing. Here, look carefully at the circuit. We have added an input capacitor Cin and a load capacitor Cl. The input capacitor together with the R1 and R2 acts as an high-pass filter. This means that the lower frequency signals are attenuated. And the load capacitor together with the RD creates a low-pass filter. This means that the higher frequency signals are attenuated. So what frequency remains? Only the frequency after the high pass filter and the frequency below low pass filter. That's why this entire circuit behaves as a bandpass amplifier. So the total transfer function is given by this formula. You can actually think of this as amplifier into high pass filter into low pass filter. This makes the mathematics extremely intuitive. Let's try to design one. Quick note nowadays, if you are wondering why we are directly using VG to be 433 millivolt, we actually calculated that in our previous common source amplifier video. Click the I button on the top right corner and watch the video first. And then come back here, it will make this entire design much easier to follow. Now let's design a bandpass amplifier having a lower cutoff frequency at 1 kHz and higher cutoff frequency as 100 kHz. And let us assume the R1 to be 100 kilo ohms, VG to be 433 millivolt, and our VDD is 1.2 volt and our RD is 1 kilo ohm. Substituting this value, we found the R2 to be 177 kilo ohm, and by substituting it in the RC frequency formula, we get the Cin to be 2.5 nanofarad. And similarly for the low pass filter, we are substituting the value of 1 kilo ohm in the RC frequency formula and we get the CL to be 1.6 nanofarad for the higher cutoff frequency. So now let's try to simulate it in Cadence and verify whether we got our output. Open your Cadence and this is a circuit. I have entered all the capacitor value and the resistor value here. To simulate the circuit, check and save, launch, ADL, choose your analysis as AC. Here since our lower cutoff 1 kHz, I am choosing the start value to be 100 and the higher cutoff frequency is at 100 kHz. I am choosing my stop value to be 1 mega. Click OK. Run your simulation. Result, direct plot, ACDB20. Click your output node. Press escape in your keyboard. Here from this graph you can see only the frequency between the 1 kHz and the 100 kHz has a gain of 10. So we have successfully designed our bandpass common source amplifier. Now you may ask me a question. Why not simply amplify everything? Because in real system, most of the signal around us are actually noise. For example, microphones only need voice frequency and radio receiver only needs one channel. A bandpass amplifier allows us to amplify only the information we care about and reject everything else. And with this video, we have completed our entire journey on the resistive load common source amplifier. So far, we have learned basic common source amplifier, biasing techniques, gain design, frequency response, and finally bandpass common source amplifier. But there is one major limitation left. The resistor RD occupies a lot of area and limits the achievable gain. So in the next video, we will take our first step towards active load and replace this resistor with something much smarter, the NMOS diode connected load. That single change will completely change how we design amplifiers in integrated circuit. So stay tuned. And as always, Noddies, keep learning, keep simulating, and keep building.